In this video we're going to look at some special bits, and we're also going to look at how to deal with rounding errors. So I have a little table here. We've got the sign, the exponent, the mantissa and the meaning. Now we've already seen the first four of these. If the exponent is all zeros, now a zero here means that it's all zeros, so we're going to have 8 zeros in the exponent, and all zeros in the mantissa, so this would be 23 zeros. And the sign is a 0, then it's plus 0. If the sign is a 1, then it's minus 0. We've also seen the denormal numbers, so if the exponent is all 0, but there is at least 1 in the mantissa, so not 0 means that there is at least one value of 1 in the mantissa. And if we have a sign that is 0, then we have a plus a denormal number. If the sign is 1, it's a negative denormal number. So we've seen these four before. Now the next four are new to us. We want to represent plus infinity, we want to represent minus infinity, and we also want to represent not a number. So we'll get into these in more detail now. So what we do is, if we say the exponent is all ones, so we're going to have 8 ones in the exponent, then we're going to have these possibilities, these four possibilities here. So if the sign is 0 and also the mantissa is all zeros, then we have plus infinity. If the sign is 1 and the mantissa is all zeros, then we have minus infinity. Now we're also interested in not a number, so that NaN stands for not a number. So you can see here where you're going to get the various possibilities of not a number. So if you have 0 divided by 0, it's undefined. N divided by 0 is undefined. 0 times infinity, infinity times infinity. Or for example, if you're looking at complex numbers, we are taking the square root of minus 1. So these are all going to come out with not a number. So in order to get not a number, we don't care about the sign. The exponent is 1. Now, not a number, we're going to have at least one value of 1 in the mantissa. And if the very first one is a 1, then we call that a quiet not a number. And if the very first value of the mantissa is a 0, then we call that a signalling not a number. The quiet not a number and the signalling not a number will be treated differently within the processor. The quiet not a number will allow the process to continue, but the signalling not a number will create a stop or a trap, and the processor will stop the process. So let's have a quick look at rounding errors. Now we've seen the number 5.2 previously whenever we did the conversion from the decimal to the 32-bit floating point binary. Now this is a 32-bit floating point binary representation here, and we've seen that it's generated as an approximation, so we get a repeating value 0011, 0011, and this will continue on forever. And as the number of bits tends towards infinity, then the value here will tend towards a constant value. But we only have 23 bits in the mantissa in order to write that value down. So what we've done previously is that we have just chopped off the last bits. So after bit 32, bit 33 and onwards just gets chopped off. So in effect this is like continually rounding down. So let's say we had the decimal number 5.79675 and we decided to round it to 3 decimal places. Well, what we could do is we could just chop off the last 2 bits here. In that case the number would be 5.796. So no matter what number comes afterwards, we're just chopping it down to the value 6. So we're always rounding down. Now this is not a good idea because you're going to get possibly cumulative errors by always rounding in the same way. So what we can do is use something called nearest neighbour rounding. So if the 33rd bit, so that's the bit that sits out with our bit stream, is a value of 0, then we can drop what is left over. So in effect we'll just be rounding down. So this is equivalent to us, say for example, having the decimal number 5.2 and we round down to the nearest 0. So this would be 5.0. Now if the 33rd bit is a 1, then what we can do is we can in effect round up. That is, we can take the value for the 33rd bit, which is a 1, and we can carry it into the next bit. But you have to note that when we carry into the next bit, we are going to potentially hit another 1, so we'll have to make that a value of 1 plus 1, which would be a 0 and a carry 1, and the carry would ripple through. Now we have one other possibility that we can deal with, and this is in effect similar to having a number like 5.5, and we have to decide whether to round up or round down, so we're exactly halfway. So if the 32nd bit, okay, so this is this actual bit here, not the 33rd, the actual last bit here that we can represent, if this bit is a 1, and the 33rd bit begins with a 1, and they're all zeros afterwards, then what we do is we round up. So in effect we take the last bit and we carry it in, and we let the carry ripple through. If the 32nd bit is a 0, and the 33rd bit again is a 1 with all zeros after it, then what we do is we just drop off everything after. So in effect we're just rounding down. So we use these three possibilities in order to ensure that we don't create accumulative errors. Now there's more ways of doing this in the IEEE standard. Finally, let's look at the truth table for the rounding. Now we have a 32-bit floating point binary number here, so that's bits 1 all the way up to 32. Now the 32nd bit here is the least significant bit, and this 32nd bit is the column here, so this is the least significant bit column. Now the very next value after the 32nd bit is the 33rd bit. Now we can't see the 33rd bit here because it's not part of the floating point number, but if we do any arithmetic manipulations, then we'll have access to that bit. So that bit's called the guard bit, and the guard bit's given in this column here. Now the very next set of bits after that are the sticky bits. So what we do is we OR those sticky bits together. Now if the value for the OR is a value of 1, then we set the rounding to a value of 1. If the value of the ORing of these sticky bits is a value of 0, then the rounding is set to a value of 0. So in effect, this tells us whether we're in a halfway position or not. If all of those values are after the guard bit are all zeros, then we're exactly halfway between values. So that's this column here. So there's in effect 3 inputs. So if there's 3 inputs, there's 8 combinations. And these are all the 8 combinations here. So finally we have our output, and output tells us whether we increment by 1 or we don't increment by 1. So +1 is increment and 0 is no increment. So let's have a talk through these. First of all, we'll leave out the least significant bit for the moment because the least significant bit only comes into play for these 2 values here, which I've written down as the tie values. So these are the in-between values, if you like, the 5.5 values. So let's look at the guard bit first. If the guard bit is a 0, so there's 1, 2, 3, 4. The guard bit's a 0, then we do not increment, so that's a 0 for the increment. So that's 4 of them dealt with. Now, if the guard bit here, for example, is a 1, and you've got the guard bit down here as a value of a 1, and you can see that the rounding bit is a 1 as well, the rounding bit is a 1, then we round up. So you can see we've got the value 1 and 1, so we're going to round up. So this is equivalent to us in effect having the number 5.6, and we're going to round up. Now, the only other two to take care of are the tie positions. So in the tie position here, we've got a value of 1 for this guard bit, and we've got a value of 0 for the rounding bit. So all of the remaining sticky bits were all zeros. So therefore, the final bit, when these bits are OR together, we get a value of 0, so the rounding bit goes to 0. So in this case here, we've got a tie. This is our 5.500000, and we're wondering whether to round it up or round down. So in this case here, what we do is we then look at the least significant bit. So if the least significant bit is a 0, then we round down, meaning that we don't add 1 onto it. And the reason why we do that is that by doing that, we are rounding to the even value. Now we know it's an even value because if the least significant bit of a binary number is a value of 0, then you've got an even number. For example, 4 is 100 and 2 is 10, but 5 would be, say, 101, so the last significant bit was a 1. So if the least significant bit of a binary number is 0, it's an even value. If it's 1, it's an odd value. So this is a rule here for the rounding to even. Now we have one other possibility when we round to even. We're obviously going to have the 1 here for the guard bit. We're going to have the rounding bits are all zeros, that the sticky bits are all zeros, therefore the rounding is 0. But in this case here, we have to again look at the least significant bit, which is the 32nd bit. And if the least significant bit is a value of 1, then what we do is we add 1 to it. So by adding 1, it means that we're going to have 1 plus 1 would give us a value of 0, and we would carry the 1 out. So it would mean that we would again get an even value. So for example here, if we were carrying the 1 in here, then it would be 1 plus 1, and this would give us a 0 in the 32nd bit, and we would carry that 1 over. So that would ensure that this value for the 32nd bit, the least significant bit, would be a 0, which would ensure again it's an even value. So by doing this, we're making the assumption that half of the time we're actually going to have an even number and also have an odd number. So it means that whenever we round to the even, we will be rounding down half of the time and rounding up half of the time, statistically speaking. So that covers everything we need to know about the rounding. So finally, we'll just mention about underflow and overflow. So we have the real number line here, and we have the limits of the floating point number system. So we can see here that we've got 0 in the middle, so we're able to represent 0. We're able to represent a number for plus infinity and minus infinity. We can represent not a number as well. Now we see that we can represent a set of positive numbers which are expressible in terms of the floating point number system, and we've got a set of negative numbers. But if the positive numbers get too large, then we're going to have a positive overflow. So we have a positive exponent in effect that's too large to fit in the exponent field. And the same for the negative. In this case we've got a negative exponent that's too large to put in the exponent field. The exponent field's only got 8 characters in it. Now we could make a larger number if we have a larger field, so rather than having a 32-bit floating point number, we could have a 64-bit floating point number, and we could have a larger exponent field and also a larger mantissa field. So we also have these things here called positive underflow and negative underflow. And this is a problem with representing numbers that are not too large but are too small. So we're going to get a positive underflow if the positive fraction is too small to be in the mantissa field. Now again, we could represent even smaller numbers if we increased the length of the mantissa field. So rather than representing numbers that go down to 2 to the minus 23, we could represent numbers that go down further by increasing the mantissa field. Now the same thing happens for the negative values. The negative fraction is too small to be in the mantissa field. So these are quite obvious from what we've learned previously. Now a good exercise is to find these points here and actually put the values in. So I'll leave you to do that yourself from what you've seen in the previous videos. So that's all for this video. Thank you for listening. I'll get you on the next video. Goodbye.